Good morning, lads and ladies. Welcome back to Calc 1 Honors. Today is your day. It is our review for exam 3, and we can talk about whatever you guys want to talk about. I'm thinking specific problems would be best, but if you want to talk about concepts or anything else, that's all up to you. So please, if you could, go ahead in the chat, start just listing problems you want to see or things you want to talk about. I will run through them in the order received in the chat, and that will be our day. While you guys get those things in, I'm going to go ahead and reply to this email. I don't know if you saw the this is so weird. So we got a different email from okay. All right, so the thing I've been trying to button up here, there've been some issues. I posted that survey link for you guys, but the AQ folks have been having a bit of a hard time getting everything to work. I'm not sure why. Sometimes they're not the most tech savvy of all humans. They are good folks, but you know how it is when older folks try to use technology. Sometimes we slip up a little bit. Oh shit, no. Service center, I'm sure this is it. Okay. So let me get this. They said they're giving me a new direct link. So I did post that SurveyMonkey link for you guys. If you would be willing to fill that out, if you have time, I would definitely appreciate it. But if you do not have time, I totally understand. So no stress. I'm going to go ahead and update that link, and then we'll get started here. Sorry about this. We can run a little bit late here to compensate for the time we're losing, but this is one of those things that for this professional development, the new administration of the college is it's a big deal. So I am trying to get some actual responses on this. Okay, so I've updated the SurveyMonkey link in that announcement. If you have time to get in there and do it, I would appreciate it. If you don't, I totally understand. Let's do some reviewing. So we do have some requests in the chat here. Number 7 from the study guide, homework I assume that's homework 13, numbers 6 and 9. So we'll get started with the study guide problem, and I'll just move through these one at a time. So surely that booted me out. That's just tradition. At least we're not getting that bad portal thing anymore. All right. So you guys are down here. Let's do it. Number 7 from the study guide. Now, of course, I don't like doing exact study guide problems, but I can take a look at a similar problem. They ask us to sketch the area represented by the function g of x, and g of x here is defined as an integral. So this is SG3, problem 7, and we want to sketch the area represented by function g of x. And I'll make mine a power function too, about something like that. We can say it's the integral from 1 to x of t cubed is just so similar. Yeah, okay, we'll do t cubed. So the game here is that this function g is defined as an integral from 1 to x of some other function. Call this f of t. F of t here is t cubed. So let me say, okay, f of t is t cubed. And I'm going to draw the graph of that function. And we know what the cubing function looks like. It's an odd function. It has this kind of shape. Something like this. So if I mark this as 1, and maybe something over here as like x, then g of x is the integral from 1 to x of f of t, which is the area under f of t from t equals 1 to t equals x. So remember, this is the t-axis. So the area represented by g of x would be something like this. So that's our first part, right? You sketch the graph of the integrand. In this case, I use t cubed instead of t squared. And then you make sure that you're shading the region described by the integral, which is from 1 to x. Now, x here is a variable, which means this really is a function of x. If x is equal to 1, then this area is 0. If x is equal to like 1.5, then this area would be a little bit smaller. If x is equal to 2, then the area would be, about what it is here. This looks like x is about 2. So the latter part of the question is asking you to kind of try to figure out a little bit more about the function g. They want us to say, find g prime in 2 different ways. We can use the fundamental theorem of calculus, FTC1, or we could calculate the actual integral here and then use, we can calculate the actual integral here by FTC2 and then differentiate. So we're going to find g prime 2 different ways. A by FTC1 and B by differentiating after using FTC2, oh, sorry, this should be FTC1. Sorry. Yeah, FTC1, and then B, by differentiating after using FTC2 to evaluate the integral. I'm glad you asked for this problem because it's one of those that could be done where you can type in the right answer without really understanding what's being asked. And there is some depth here. There are reasons to attack this two different ways because it kind of helps you see the connections between FTC1 and FTC2. Recall that FTC1 says if call it capital F of X is the integral from A up to X of little f of t dt, then big F primed of X is just little f of X. All right, so if you have a function that's defined as an integral from some constant up to X of some other function, and you want to differentiate this guy, the integral just goes away and you plug in this upper bound here. So in part A, by FTC1, g primed of X here should just be the integral goes away and I plug this variable in here, should just be X cubed. That's FTC1. On the other hand, by FTC2, g of X itself is the integral from 1 to X of t cubed dt. Remember what FTC2 is, it's the tool that says you can evaluate integrals by taking antiderivatives. So this should be equal to an antiderivative for t cubed, which is t to the 4 over 4, evaluated from 1 to X. So this is what I want to differentiate. I'm just basically simplifying this function. The way I'm simplifying this function is by carrying out the calculus operation that's used to define the function. And then I'm going to differentiate the result. So before I'm allowed to finish up here, I have to plug in. So this is going to be X to the 4 over 4 minus 1 to the 4 over 4. So g of X is just X to the 4 over 4 minus 1/4. That's FTC2. Therefore, g primed of X is the derivative of that. Well, if I differentiate this, I get 4x cubed over 4 minus 0, right? The 4 down here is a constant multiple. You don't need any quotient rule or fancy shit like that. You just differentiate this guy. The 4s are going to cancel, and 0 is 0. So this is x cubed again. And thank goodness mathematics works. We got the same thing either way. Do we understand what's going on here? Are there questions about the significance of this problem, or why we get the same thing, or what the difference is between the two mechanisms? It depends on what the question asks. If I say, use FTC1 to find the derivative of this function, then you just have to use FTC1. That's it. And it's super easy peasy. If I were to just give you this function and say, calculate the derivative without any sort of do it via this rule, you could do it either way, and that would be fine. I would not likely ask you to do both on a test, but you should be aware that I could give you an FTC1 problem that was a little bit more complicated. So I want to look at a slight variation on this that we could see. In other words, don't forget how the chain rule interacts with FTC1. So an example of a test question that's relevant here, I could say, let g of x be the integral from, 0 up to x squared of what's something we don't know how to integrate, the natural log of t dt, and find g primed of x. So this is a problem I could give you on the test. And here I haven't given any instruction as to which mechanism you should use. Do you evaluate the integral and then differentiate like part B? Or do you use FTC1 like in part A? In this particular case, you guys don't know how to do this integral yet. This integral requires integration by parts. It's not something we learn in Calc 1. So FTC1 is the only viable path for us. If I saw someone doing integration by parts here, it would be an immediate clue that they cheated. So in this case, we would need to use FTC1. By FTC1, g primed of x, just like the last problem, the integral goes away, you take this thing and plug it in here, would be the natural log of x squared. But the reason I wanted to show you this is because there's a little bit more. By the chain rule, because this isn't just an x, this is an x squared, kind of, this is your inner function, you would need to multiply by the derivative of x squared. So I give you the natural log of x squared times 2x, and that would be your answer. So yeah, on a test, you wouldn't be required to show both, unless for some sadistic reason I said you need to do it both ways, but I wouldn't do that. I am interested in making sure you know how FTC1 and FTC2 work, but I will test those on separate questions. And with regard to the sort of challenging things I could do with FTC1, this is about as bad as it could get, right? Where you need to use FTC1 together with the chain rule. Any questions on this or the previous example? All good. Okay, cool. So then I will move forwards. Homework that's homework 6, no, or sorry, homework 13, numbers 6 and 9. Am I understanding that right, Kevin? The most recent homework, those two problems? Yeah, okay, let's do it. Okay, so they've given us two curves here, y equals sine x and y equals 3x, and they want us to find the area of the region bounded by those curves from x equals pi over 2 to x equals pi. So first we need to sketch the region, where all these area between curves problems, they follow the same sort of algorithm. Sketch the region, determine whether you're working with respect to x or with respect to y, and then set up and evaluate your integral. So this is homework 13, problem 6, and we want to find the area of the region bounded by y equals sine x and y equals 3x from x equals, what was it? 2 pi? Pi over 2 pi. So I need to begin with a sketch of sine x and 3x. And I'm going to do my best to draw these to scale. But unfortunately, y equals 3x, it grows much larger than sine x. So this is going to look a little bit silly, but I'll do my best here for you. If this is pi, then this would be pi over 2. Mark this is 1, and this is -1. The sine of 0 is 0. The sine of pi over 2 is 1, and the sine of pi is back to 0. So the sine function here would look something like this. And then something like this. from 0 to pi, roughly. And then y equals 3x. It's going to look, I'm going to be like way out of space here. Something like this, if we insist on doing it to scale. Or even roughly to scale. So here we are, because 3 pi is like 9, right? So the area I'm looking for is the area between these curves from pi over 2 to pi. That's going to be this stuff. All right. So the upper curve here is definitely y equals 3x. The lower curve here is y equals the sine of x. And because there is throughout this whole region a clear upper and clear lower, these are both functions of x, there's no reason to ponder about like turning things sideways and working with respect to the variable y. I could draw in a little strip if I wanted, a little representative Riemann rectangle. And you see that something like this would work just fine all throughout that region. No question, as I slide this back or forth about what the upper and lower would be. The upper is always y equals 3x. And the lower is always sine of x. So the area here would be the integral from pi over 2 to pi of 3x minus the sine of x dx. So remember the trick is we're always going to integrate either upper minus lower or right minus left. If there is a clear upper and lower, if all the functions are functions of x and we can figure out how to set it up that way, that's usually the nicer way to operate because that's what we're used to. And that's the case here. Questions about how we arrive at the integral, how we get to this. All right, then. The next step would be to find an antiderivative. That would be 3/2 x squared. An antiderivative for sine x is negative cos x, so this would become plus cos x. And that's evaluated between the bounds, pi over 2 and pi. So continuing down here, I'd have 3 pi squared over 2 plus the cosine of pi. And then from that, I need to subtract all of 3/2 times pi over 2 squared plus the cosine of pi over 2. So not much left to do. We just need to say what the cosine of pi and the cosine of pi over 2 are. You guys all survived my interview last semester. So what is the cos of pi? Quiet day, but we're in the chat. Yeah, okay. So the cos of pi is -1. And the cos of pi over 2? This fellow is 0. Excellent. All right. So we have here 3 pi squared over 2 minus 1 distributing this negative, I'll have 3 pi squared over 8, 2 times 2 squared. And that's it. You could combine the pi squared terms if you wanted. 3 pi over 2, 3 halves minus 3 eighths. That's the same as 12 eighths. So 12 minus 3 is 9. So this is 9 pi squared over 8 minus 1. Any questions on this fellow? All right, moving on. Oh, why is it 9? So 3 pi squared over 2, I'm writing with as a common denominator with this. So I multiply top and bottom by 4. So 3 pi squared over 2 is the same as 12 pi squared over 8. And then 12 pi squared minus 3 pi squared is 9 pi squared. If you gave me this on a test, I would accept it. But nice to combine like terms when we can. And since these are both products of or have factors of pi squared, we can put them together. All right. So charging ahead. I'm saying this number 9 from the same homework set. Yeah, this one's a little more challenging. So here, there is room for uncertainty as to which variable we should operate with respect to. And that's still not correct grammar. Which variable we should operate with respect. I hate that grammar again, but yeah, 2x plus y squared equals 8 and x equals y. So I'm just going to write it 2x plus y squared equals 8 and x equals y. You guys know what we want to do. We want to find the area of the region enclosed by these boundary curves. And I think the challenge is in graphing. The fact that the y here is squared is enough to tell me that this apparatus is not a function of x. If you have an even power of y in an implicit expression, then when you try to solve for y, you would get a plus and a minus, which means you're going to have some symmetry about the x-axis, which means you're going to fail the vertical line test. So the y squared here tells me that I'm going to be working with respect to y, meaning I want to think of these both as like x equals something. I want to think of y as the variable. The independent variable is y, and the dependent variable is x. In other words, we're kind of turning our heads sideways. So my very first move here would be to solve this guy for x. This is the same as saying x equals 1/2 times 8 minus y squared. And I subtract the y squared and then multiply both sides by 1/2 to get x alone. And the other guy's already solved for x. It's also already solved for y. But yeah. Okay. So next step is to draw the graph. If I go looking for some intercepts, this guy over here is a parabola. The y squared tells me it's going to open sideways. I can find the x and y intercepts pretty readily. If you plug in y equals 0, then you get x equals 1/2 times 8, which is 4. So the x-intercept is 4, 0. Actually, I'm going to need more space on this side. Yeah. So we'll call this 4. So 4, 0 is on the graph because when y is equal to 0, x is equal to 4. And then if I want to look for y-intercepts, I could plug in x equals 0, and we see that that would mean 8 minus y squared is 0. The square root of 8 is 2√2. Between 2 and 3. I'll just call it the square root of 8 because that's what it is. And the other one down here would be negative square root of 8. So my sideways parabola is looking something like something like this. Modulo my bad art. And then y equals x, x equals y, those are the same. That's a line through the origin with slope 1. Ooh, I needed more over here. All right, doing our best to draw to scale. Here is x equals y. Here is x equals 1/2 8 minus y squared. And remember, the graph of that parabola, the way we got it was by plotting intercepts. That was the easiest way here. If you don't remember much about conics from pre-calc, or your pre-calc class didn't do conics in a lot of detail, the fastest, cheapest, easiest way to get a graph of a wonky sideways parabola like this is to plot the intercepts. Remember, once you know 3 points on the graph of a parabola, that entirely determines the parabola. So you can always get a good picture from 3 points. The region whose area I'm after is the region in here then. So this is the area I'm looking for. And because we know we're working with y as our variable, we know we're going to have to integrate the right minus the left from whatever the smallest y value is in the region to whatever the largest y value is in the region. So a few things we need to do. This will be my right function. And this will be my left function. Because everywhere within this region, if you look at any particular y value, this is to the right of this. Your little Riemann representative strip or Riemann representative rectangle would look like this. Well, you could draw it in anywhere. As long as it's horizontal and within that region. All right. What else do I need to do before I can set up my integral? Now I'm going to integrate right minus left, so I'll be integrating 1/2 8 minus y squared minus y. But what else do I need? Bounds. Good. Where do I get the bounds? They will be y values. Yep, certainly they will be y values. Where do those y values come from? They're the y values of what points? Excellent. The intersection points here. So to find these, we set the two functions equal to each other. We set y equal to 1/2 quantity 8 minus y squared. And I need to solve this for y. So I multiply both sides by 2. And then I can add y squared and subtract 8 from both sides. That'll give me y squared plus 2y minus 8 equals 0. In the worst case scenario here, you can use the quadratic formula, but if we're lucky, this guy will factor nicely. So I need two numbers whose product is -8 and sum is +2. 2 and 4 work. So this is y plus 4 times y minus 2 equals 0. So y equals 2 and y equals -4 are the y values at those points. And although we don't need them, we can find the x values also. Remember, these are intersection points from the line x equals y and the parabola x equals 1/2 8 minus y squared. So in particular, we're along the line x equals y. So at any point along the line x equals y, the x and y values match. That means the point up here is 2, 2. And the point down here is -4, -4. But we only really needed the y values. So then my integral is going to be the integral from -4 to 2 of the right function, 1/2 8 minus y squared, minus the left function, which is just y. And it's a dy integral. That's what we mean when we say we're working with respect to the variable y. Things from here are not bad. We're integrating a polynomial, so the game is mostly about the picture and the setup. I will be requiring you to draw pictures like this on your test. So make sure as you solve these problems, I know I've said this all semester, but I cannot say it enough. You need to practice graphing these things by hand, and make sure you can do it without leaning on a graphing calculator or a tool like Desmos. It's okay to use those if you're stuck on the homework, but you need to develop the graphing skills. So any questions up to here, up to the integral? Everybody good? Oh, baby, we got an Amazon package. It's okay, but I know, I saw her. She's okay though. She's bringing us shit. It's nice. All right, sorry about that, guys. So from here, we just do the integral. I can distribute the 1/2, and we get 4 minus 1/2 y squared minus y dy. If there were like terms we could combine, we would, but there are not. So this has as an antiderivative 4y minus 1/6 y cubed minus 1/2 y squared. And we evaluate that from -4 to 2. When we plug in the upper bound, we got 4 times 2 minus 1/6 times 2 cubed minus 1/2 times 2 squared. And we subtract from that what we get when we plug in the lower bound, which is 4 times -4 minus 1/6 times -4 cubed minus 1/2 times -4 squared, close, close. And now it's just a matter of cleaning things up. 4 times 2 is 8 minus 2 cubed is 8, so this is 8/6 minus 1/2 times 2 squared is 1/2 times 4, which is 2. And now distributing the negative here, 4 times -4 is -16, so this is going to become plus 16. 4 cubed is 64, so this is -64/6. But the negative here makes it positive, and the negative here again makes it negative, so make sure you're very, very careful. -4 cubed is -64. -1/6 times -64 is positive 64/6. And distributing this negative, it becomes negative again. So this is minus 64/6. Then finally here, 4 squared, -4 squared is positive 16. Positive 16 times -1/2 is -8. -8 times this negative is positive 8. So there's your answer. And we can try to clean this up again as much as possible. 8 and 8 is 16. The two outer terms there add up to 16. 16 and 16 is 32. Minus 2 is 30. So the integers here add up to 30. And then you've got negative 8/6 minus 64/6. So that's negative 72/6. And since a person who is 6 feet tall is 72 inches, 72/6 is 12. So that's 30 minus 12, which is 18. So that area there is 18 square units. Questions about this fellow? All right, moving right along. Where are we here? That was homework 13, number 9. We want to look at number 2 from the study guide. I'm happy to talk about study guide problems, but I'd prefer not to solve the whole thing. So number 2 here, this is it, right? 2 here, we're working with this cosine function. So let me remind you kind of how this would work. I know you're saying that you're comfy with the process, but the answer is wrong. It's kind of hard to weed out exactly where things went astray without having work to look at, but I can set up a similar problem. This is also, actually, this is one we've done in class before. I don't mind going through this. So it's 3 cosec from 0 to 3 pi over 4 by R6. So find R6 for f of x equals 3 cos x from on 0 less than x less than 3 pi over 4, right? So one thing, if you're using decimals here, and we are, because they ask us to round to 6 decimal places, make sure your calculator is in radian mode, not in degree mode. That's the most common error I see on this. And if I had to guess, if you feel like you're doing everything right, but your answer is coming out wrong, it's probably because your calculator is in the wrong mode. So if you're using a TI, something like this, you go to mode, scroll down here, you see you've got the option between radian and degree. Make sure you're in radian mode. R6, so we can draw the picture here. I'll leave that to you guys. R6, remember, is the sum from I equals 1 to 6, f of xi times delta x, where delta x is b minus a over n, and the xi's are a plus I times delta x. So delta x here is 3 pi over 4 minus 0 divided by 6, which is 3 pi over 24. And the xi's then are 0 plus I times 3 pi over 24, which is just 3 pi I over 24. I like to list out the xi's. So x1 here would just be 3 pi over 24. Sorry, fly over here. When I is equal to 2, we'll have 3 pi times 2, which is 6 pi over 24. We can simplify this, by the way. 3 pi over 24 is pi over 8. 6 pi over 24 is pi over 4. x3, when I plug 3 in here, we would have 9 pi over 24, which is the same as 3 pi over 8. X4, when I plug in 4 for I here, that's 12 pi over 24, which is pi over 2. X5 would be 5 pi over 8. And X6, when I plug in 6 for I here, we have, what's that going to be? So 6 pi over 8. I'll just write it 6 pi over 8, which simplifies if you divide top and bottom by 2 to 3 pi over 4. Yeah, of course it does. So these are the xi's. Okay, so we got it from here. All right, just for gits and shiggles, because we are here now, I'll go ahead and write down what R6 would be. My function f of x is 3 cos x, and if you expand this out, that would be 3 times the cosine of pi over 8 plus 3 times the cosine of x2, which is pi over 4, plus 3 times the cosine of x3, which is 3 pi over 8, plus 3 times the cos of x4, which is pi over 2, plus 3 times the cosine of x5, which is 5 pi over 8, plus 3 times the cos of 3 pi over 4. All of this gets multiplied by delta x, which is 3 pi over 24, or just pi over 8. And that's what we would crunch. All right, yeah, be mindful of the mode your calculator's in when you're working on calculator-related problems. But good, okay. That frees us up to move to the next one. Is it heavy? Oh no, I was thinking it might be a rocking chair, but it's not. All right. So, homework 6, question 7, or question 8. Am I reading that right? Homework 6, Haley? All right. So always good to go back and make sure we're comfy with these older school things. Math does build. So 7 or 8. All right, let's look at 7 here real quick. So here we want to use implicit differentiation to find y double prime at the point where x is equal to 0. This is a little bit tricky. 8 is certainly easier. So we can take a quick look at either of these. We have xy plus 5 e to the y equals 5e. And we want to find y prime prime at the point where x is equal to 0. So the first thing I would do is find what is y when x is equal to 0, because I'm going to need to be plugging things in down the road after differentiating. So my first step here would be to find the point on this curve associated with x equals 0. So when x equals 0, y equals what? Well, I would have 0y plus 5e to the y equals 5e, which is the same as saying 5e to the y equals 5e, which is the same as saying e to the y equals e, and taking natural logs, we see y is 1. So x is 0, y is equal to 1. We're going to tuck that in our pocket. Now we find the differential. So I come back here and I take the derivative on both sides, the dx derivative. on both sides, and I'll be differentiating implicitly with respect to x. So on the right-hand side, 5e is a constant. Its derivative will be 0. On the left-hand side, I have quite a bit more work to do. This piece will require the product rule. So if I want to differentiate x times y, that is a product rule thing. That's the derivative of x, which is 1 times y, plus x left alone times the derivative of y. And the derivative of y, the ddx derivative of y is y primed. And then to that, I have to add the ddx derivative of 5e to the y. That's 5e to the y times y primed. So this is what I get when I differentiate the original expression implicitly on both sides with respect to the variable x. If the problem just asked me to find y primed when x is equal to 0, then I would plug x equals 0 in here. And when x is 0, we know y is 1. So I'd plug x equals 0, y equals 1, and solve for y prime. I am going to go ahead and do that because I expect I might need to know y primed when x is 0 in order to find y double prime when x is 0. Military jet's been screaming overhead all day. All right. So when x equals 0, we know y equals 1. So we get here, plugging in 0 for x and 1 for y. 1 plus 0 times y primed plus 5e to the 1 times y primed equals 0. 0 times y primed is 0, so this is the same as saying 1 plus 5e times y primed is equal to 0. We can subtract the 1 over and we get 5e y prime equals -1. And then divide both sides by 5e, and we get y prime is equal to -1 over 5e. So that would be y primed when x is equal to 0. To find y double primed, I need to take this expression and differentiate it again. So differentiate. I have ddx of y plus xy prime plus 5e to the y times y prime equals ddx of 0. And now I will get the derivative of y, ddx is y primed, plus, here I'll need the product rule. I would have 1 times y prime plus x times y double primed, plus, here I will also need a product rule. That's going to be differentiate 5e to the y, and I get 5e to the y times y primed. So this would be y primed squared. Plus, now I leave this alone and differentiate this. I'll have 5e to the y times y double primed. And on the right-hand side, ddx of 0 is still just 0. So I know it looks horrendous and scary, but we're almost done. We know that when x is equal to 0, y is equal to 1. And we know that when x is equal to 0, y primed is equal to -1 over 5e. So we plug all this in here and solve for y double prime. So I'll just write this, plug x equals 0, y equals 1, and y prime equals -1 over 5e, and solve for y double prime. This is not the only way to do this, but it is the fastest. So you could also, back at this stage, solve for y prime. and then differentiate that again to get y double prime, but you're not really taking full advantage of the power of implicit differentiation, which is that you don't have to have an explicit expression. So this, as long as it is, really is the fastest way. So once you get down here, you're ready to declare victory. You just need to plug those things in and solve for y double prime. All right. I'll hold here just for a second. And we'll move to the next fellow, which was number 8. Number 8 is definitely more straightforward. We want to find dy dx using implicit differentiation. Is good review for the final also. So I've got 4 root x plus root y equals 3. And we had 4 root x plus root y equals 3. So I will apply the differential operator d dx to both sides. And then on the left-hand side, I'll definitely need some implicit differentiation, a fair amount of work with the chain rule. The derivative of 4 root x, remember x is, this is x to the 1/2. So this will be 4 times 1/2 times x to the 1/2 minus 1 is negative 1/2. And then the root y, that's also y to the 1/2. So he'll differentiate to 1/2 y to the negative 1/2. But then because we're using the operator d dx, we need to multiply by y prime, right? Because this is implicitly a function of x. And then over here, d dx of 3 is 0. And then we can solve this for, simplify as much as possible and solve for y prime. 4 times 1/2 is 2, so this is 2 times, I'll write it as 2 over the square root of x, 2x to the negative 1/2, plus 1/2 y to the negative 1/2 is 1 over 2 square roots of y, and y prime equals 0. We can subtract the 2 over root x term to the right-hand side, and we get 1 over 2 square roots of y times y prime equals negative 2 over the square root of x. And then we can multiply by the 2 square roots of y. And since they're okay with an implicit expression, they didn't say give us an explicit expression, that will be the end. So this is negative 2 over the square root of x times 2 square roots of y. You can multiply the 2's together. So this will be negative 4 square roots of y over the square root of x. And that is our implicit expression for y primed. If we wanted an explicit expression, we would have to go back and solve this for y, and then plug that thing in here. All right. So our next one from Thomas here is number 13 from the study guide. Here, find the general antiderivative, or sorry, general indefinite integral, and then they want us to graph some things. This is an interesting problem. I don't remember who it was. Somebody brought this to my office hours, and we spent a little bit of time struggling to get Desmos to graph this function. I'll tell you, I did eventually get it to work. Instead of writing it as 1/12 cos x, if I wrote it as, or whatever it was, x squared over 12 instead of 1/12 x squared, it did work. So we want to find the general indefinite integral of cos x plus 1/4 x. That's correct, Thomas. Yeah, there won't be any implicit differentiation on Equation 3. plus x, and what is the same? 1 plus, I'll change it a little bit. How about 1/3 x dx? Evaluate and graph. So I'll tell you right now, the graph of this function is not one, the antiderivative here, the graph of the antiderivative is not one I would expect you to know. So don't feel bad using a graphing utility on this. The antiderivative is not hard to compute. Antiderivative for cos x is the sine of x plus 1/3 times x squared over 2 is the antiderivative for 1/3 x. You have your plus c. So this is sine x plus x squared over 6 plus c. And we can graph with c equal to 0 just to get a start. And again, not something I expect you guys to know, but if you want to know how I would anticipate what this graph looks like, I'm happy to tell you that. Sine x is a wave. Its amplitude is 1, so sine x is always bounded from +1 to -1. So I know I'm going to have some wavy shit whose ability to affect the shape is bounded from -1 to 1. And I'm adding that to this guy, which is a parabola. So this is kind of the dominant thing. If you zoom way out, it's just going to look like this parabola. But there will be little waves kind of making it move up or down one a little bit at each point of that parabola. So kind of think of it as a wavy version of x squared over 6. That's what I would expect. Now, it would still be, oh no, I was doing something else for another class. If I want to graph this as sine x plus x squared over 6. Here you see it, right? So kind of if you zoom way out, it just looks like x squared over 6 because the influence of the sine x is small compared to the influence of x squared. Sine x is always between -1 and 1, so it can only shift the little parts of the graph up or down at most 1. But if you look near the origin, you can kind of see the influence of that sine x a little bit more clearly. It's kind of taking this general parabolic shape and making it a little bit wavy. In particular, if you're trying to pick out the right graph, I would notice that this guy is increasing at 0. So you can compare to your other options here. Part A is definitely out because the thing is totally the wrong shape. Part B looks possible. C and D do not look possible because this guy is not increasing when x is equal to 0, right? He has a horizontal tangent line there. And this guy is decreasing when x is equal to 0. So it looks to me like it's going to have to be that guy. That's the game. All righty. Where else are we? So that was 13 on the study guide. We'll look at homework 10, question number 8 next. Come back to the level sign. Homework 10, question 8. No, Thomas. So definitely not. Never during one of our exams can we take out a graphing calculator or any graphing utility. I won't ask you to graph something unreasonable on the test. So the only things I would ask you to graph are the kind of core functions that I've told you you need to know throughout the semester. So you need to be comfy graphing trig functions, polynomials, rational functions, and that's about it. Square root functions, power functions. And translates thereof. Okay, so we wanted homework number 10, problem 8. This is a good one. So here we're told that the graph here is some straight lines and a semicircle. So this is the semicircular bit, and they're telling us that it's a semicircle so that we're comfortable using the appropriate area formulas. And then these are, of course, the straight line bits. So that's G. And they want us to find some integrals. And remember, integrals measure signed area. So I'm kind of tuck this in the corner. I suppose I should draw a graph. So, this is 12. And mark the halfway point there at 6. This is 6, and this is 12. We have a straight line bit coming down like this. Then we have a semicircle centered at 12, whose radius appears to be 6. So if we look this as -6, up and down as far as -12. Oh, I didn't need to do that. No, okay. Just this. There's my semicircle, and then off to the right. Only go out here to 21. So this would be 18, because we're distance 6 from the center. We call this 21, and they go up 1 tick mark there, which would be 3. All right. So the point here is 21. 3. They want us to use this to evaluate the integral from 0 to 6 g of x dx. This is the graph y equals g of x. They want us to evaluate the integral from 6 to 18 of g of x dx. They want us to evaluate integral 0 to 21 of g of x dx. And they want us to evaluate the integral from, oh, that's it? Is that it? Just those 3? 6 to 18. Okay, so here's the game. Integral 0 to 6 is the area, the signed area bounded by the graph of g and the x-axis from x equals 0 to x equals 6. So this area right here that's the integral from 0 to 6 of g of x. That's part A. So we can use geometry. That's the idea. Each of these can be solved just by using some formulas from geometry. This is the area of that triangle. Because this is a straight line, this is a little right triangle. So its area is 1/2 the base times the height. The base here is 6, and the height here is 12. So this is 36. They ask for the integral from 6 to 18, which would be just the semicircular bit here. That semicircular bit lives below the x-axis, so the integral will measure its area as negative. And then it is a semicircle, so the area is going to be half of the area of the full circle. The full circle would have area pi r squared. So this is going to be 1/2 times pi times whatever the radius is squared. And if we look at the circle, the center is at 12, 0, and this far edge over here is at 6, 0. So the radius is 6. So this is negative 1/2 pi times 36. So that's negative 18 pi. And that's the integral just from 6 to 18. And finally, the integral from 0 to 21, the nicest way to do this, since we've already done 0 to 6 and 6 to 18, is to say, okay, this is the integral from 0 to 6 of g of x dx, plus the integral from 6 to 18 of g of x dx, plus the integral from from 18 to 21 of g of x dx. In other words, the whole integral is the sum of this, this, and this. Since I've already computed this and this, I really just need to compute this. First, let's write down the ones we know. The integral from 0 to 6 is 36. The integral from 6 to 18 is negative 18 pi. And then this last guy, sorry, I'm losing out a little. And then this last guy is, again, a little triangular area. So the integral from 18 to 21 of g of x is 1/2 this base times this height. The base here from 18 to 21 is that 3? And the height is 3. So this is 1/2 times 3 times 3. Or I'll write it like that, 1/2, 3 times 3. But of course, that's 9/2. So this is 36 minus 18 pi minus 9/2. And you could combine those if you wanted. At least the 36 and the 9/2 I would probably combine, but this is good. This is also fun. These are fun problems. And the point of this problem is twofold, kind of to get comfy with the idea of a definite integral as a signed area, and also to practice the rules for integrals, like splitting things up. Oh, yes. This is positive. I'm so sorry. Yes, positive. All right. Oh, and I think with that, we are out of time. I think we're exactly out of time here. I know there are some problems in here we did not get to. Where did we get up to here? So 13 from the study guide and homework. Oh no, we did do those. Okay, yes, I think we got most of this. Are there later problems given? Homework 11, number 1, part B. Okay, let me take a quick look at that, just so I can, I don't want to leave anybody hanging. Homework 11, number 1, part B. So they say estimate. Yeah. Okay. So this is one that I have to go back and add things in for you guys. We haven't even talked about the midpoint rule. Don't worry about it. It's not something I'm going to test you on. If you know the left and right Riemann sums, I'm happy. The midpoint rule is where you, instead of using the left or right endpoints of each subinterval, you find the dead middle of each little subinterval, and then you use that for your height. It could be done, but it's a pain in the ass, especially for G of 28, because here you have to work with the graph. It looks like the dead midpoint would be right here. So that height would be given by this. So if you wanted to define the integral from 24 to 28 and approximate that piece by the midpoint rule, it looks to me like you would use whatever this height is here. So if that's 4, it's probably 8. So this would be your little rectangle here. But don't worry about it. I'm going to go back and add in the points for part B. I did my best to curate these problems and get rid of anything with midpoint rule stuff, but one of them snuck in. So I do apologize for that. Don't panic. Yes, I will go ahead. So I cleared extension requests yesterday. I will clear them again today, right now, before my office hour starts. Is there anything else that we want to ask before we conclude for the day? All right, then I will go ahead and clear these extension requests first thing. That is it for me. I do have my normal office hour today from 1 to 2 p.m. So if you want to talk more, you can come see me there. Otherwise, I will see you guys for the test on Monday. Take care.